So, dear students, let us start with the topic of gravitational field and satellite motion. Yeah, about this topic, to give you the highlight, it's going to be a very long topic, and we are going to do it in 2 to 3 videos, which we are going to talk extensively on what is needed on the gravitational field according to the syllabus. We are going to talk about Newton's law of universal gravitation, which I believe you might all have studied in early classes. So we take it slide by slide as usual. And like I do say, for the illustration part, you need to do more numericals, or you also watch the videos on the that is based on numerical and solving questions on it. So, guys, let us start with the topic. And about the topic, we introduce ourselves to gravitational field and introduction and Newton's laws of gravitation. About gravitational field, to have an understanding as we progress in the topic, I'm pretty sure you are going to increase your level of understanding under this topic. We can define gravitational field, as you can see showing at my back, as it's just a region. Let's just put on a note. A region where gravitational force, that's another way to define, where gravitational force is experienced, where gravitational force is experienced due to due to the force of gravity, due to the force of gravity, and obeys the inverse square law. The inverse square law. So what we are trying to say is that when we give definition to a field, generally there are different type of field under the Newton laws of motion. We've talked about that, and different type of forces. So where force is experienced on a point mass, or due to the force of gravity acting on the body, or the bodies, as the case may be, is what we call the field. So when we talk about obeying inverse square law, what we're trying to say is that what we need to understand the particular law that follows the law of what gravitational fields. Like I said, as we progress in this topic of gravitation, you are going to have deep understanding on other things that is needed for definition and other characteristics in which the field depends on. Now, for now, we are limiting ourselves to the syllabus, and I said I will take it with respect to the slide that we have that has been provided by the student for me to talk about. So the next we talk about here, not to waste our time, there are other factors, there are a lot of factors that affect gravitational fields, which we are going to talk about. I presume, I hope, if it is in the slide, talking about the lines we use to represent the field. You know, you can't have a field without having a line. But be that as it may, for now, I am going to limit myself to what I have on the slide only. And about this now, after the definition or introduction to it, so what I want you to know that a force field, generally, you can also keep in mind, which I believe in your early classes you have studied, that a force field or generally force field are vector quantity. So you can also write that what they have both magnitude and direction. So this is also very important for you to keep at the back of your mind. So I hope you are following, and I hope you are getting what we're talking about. So it is a force field because force is experience. That is what makes it a vector field. So they have both magnitude and direction. So the next point we are going to talk about in this slide is what we call the Newton laws of gravitation. Now, about Newton laws of gravitation, I believe you might have studied in early classes. We can just write that it explains. I think it's better to put down a note. It says it explains the relationship of the type of force, of the type of force that exists between point masses, point masses separated by a distance. So, and about that, if you want to keep down a note and you are asked to state the Newton's law of universal gravitation, I know all of us at this level should be able to state the law. What the law is talking about is what there exists a force, and the force that exists is generally or mostly called what attractive force. Student can keep that in mind. The force that exists between what point masses is what we said attractive force. In our junior classes, we might have studied, like I do say, that we can relate the Newton law of gravitational in two ways. He said when you have two bodies, let's just take an illustration, 2 point masses. I'll take the first one as m1 and the second point mass as m2, separated by a distance. They are separated by a distance. We use r generally. It's not necessary you use r alone. You can use other things. The 2 point masses are separated by a distance r, as you can see. So he said the force acting between them, there's going to be an existence of a force acting on the first one due to the second one, the force acting on M1, force acting on M1 due to M2, and the force acting on M2 due to M1. So there exists an attractive force in between what the point masses. This attractive force will be equal and opposite according to Sir Isaac Newton third of third law of motion. So the force acting between F1, you can say this force is F1, and the force here we say is what F2, which you can write from your knowledge of motion as a F1 is equals to negative of F2, and you put this in modulo, you know it will be equals to F2. So the total force that exists between point masses, you can write as F. So there is a force that is generated on M1 due to M2, and the one generated on M2, which we call F2, due to M1. So these forces are equal and opposite according to Sir Isaac Newton law of motion, and the general force that exists between them are equal. So we say the modulo of the two force here, we call it what? This. Force is a vector quantity, you can put arrow on top of it. So I believe you have studied these in early classes, and what he stated was that the force, which is the resultant force that exists between these two forces that are equal and opposite, is now given in two conditions. He said the force is directly proportional to the product of their masses, we say M1 and M2. He also stated that the force is inversely proportional to the square of their separation, which we call the inverse square law. Later part in the word syllabus, you are going to understand some other thing with respect to gravity and other things. That is why I am not taking my definition with respect to gravity now, because we are still going to talk about gravity and the weight that acts on the body. We have learned from mechanics that the weight of the body always acts downward, but we should also might have learned in mechanics, which I believe that the variation of G will vary from one place to another. So going back to what we are studying now, we can combine these two. This is just a variation relationship in your mathematics. And directly you can say the force that exists, which is what we are talking about, will now be equals to, there will be a constant we call what? G, capital letter G. Then you say M1, M2. You are dividing this by r square, which is the radius. So you have this divided by r square, and this particular formula or law is called what? The Newton's law of what? Universal gravitation. Another important point that is important here is that this G, which is a constant, is called, is called the gravitation constant. We say gravitational constant, and there is a constant for all these on the surface of the Earth. You are living in the planet Earth. When we get to satellite motion, you are going to understand some other things. Now, gravitational constant G is given by formula as a constant parameter, which you can keep in mind. I think is 9.11 times 10 to the power negative 11. I hope I get that. And if I did not get that, you can always what check your constant physics table formula. It is always going to be given in your calculation. So that is that about that. I said it's 9 point. I'm not sure it's 9.11. So now I don't even remember. So it it happens sometimes. So 9 point. No, that's 9.11. Should be 6.67. Now it has scored. That is one thing about when you have the knowledge. It is always what in you. 6.67 times 10 is negative 11 Newton. You can see you can try and make gist of a formula if you don't know how to cram. Somebody like me don't cram. I know them. So I can actually get the SI unit by what I have here. So I have Newton meter square per kilogram. So I think this is it. Newton meter square per kilogram. If I make this, it will be G, then this is R square, then Y, this is what per kilogram. So this is the way we relate that, and this is the formula you can always keep in mind, and this is what they call the Newton law of gravitation. So this G is always a constant, and that is that about that. So we move to the next slide. Wow. And about the next slide, we have what we call the limitations of Newton's laws and the extended body. Now, as we have stated in the previous slide, that Newton's law, we can keep down a note for understanding's sake, that Newton's law of universal gravitation, Newton's law, only valid, please, I'm going to be using abbreviation, only valid for point masses. When I say point masses, I mean shorty masses, that is small mass, and will not work for an extended body. So this is one of the limitations if you ask. And Newton law of what universal gravitation or Newton of gravitation only work for point masses and does not work for what we call extended bodies or heavy mass. We can take into illustration to understand what we're talking about. That as we have already studied that when we consider, let's take for instance, uh, a particular part that has a big mass. We are computing that with a point mass m. We call this one m1, and we say we want to calculate this particular the distance at which you can say this is having an heavy mass. This is a big what an extended body with big mass. So if we say these two bodies are separated by a distance of I'm not going to scale r from each other. So let's say the mass of this one is m2, or you can take this as m1 or m2. It doesn't change anything. So because I know students will say, why is this one not m1 and this is m2? It does not have any effect. So this is a point man. This is an extended body. Now, what you need to know is that for these big bodies, if you say the force acting between them, which we call by F vector or F, which is you can say in vector form, it will be different. I'm still coming to that. Gm1 m2 by r squared. We are saying this for an extended body. This expression is very, very wrong, as Newton law does not work for big masses. It only works, the force of attraction that exists between bodies is only what for shorty masses. So keep that at the back of your mind. And if we want to get the force of attraction that exists between extended bodies or masses that are big like this, what we do is what we only take a section. We take a section in the body, a very small point in the body, which we call what? We call that particular section a simple section we call the hem. And when we say we are taking a part out of a whole, we surely know that if we take a part out of a whole, it is going to what? It is going to be what? Integrated. So always keep that at the back of your mind, that whenever we have an extended body, what we do is what? We take that extended body, then we take a distance from that what I said we take a elemental part of that extended body. That extended body. We are going to take an elemental part, and this elemental part, we are going to what? Take a distance of separation from the elemental part to the point mass because it is normal, and there will be a force of attraction that will attract itself towards the what? The direction of what? The direction of the point mass. So the force we act in this, so which we can call the force acting here, we can call it the F, and we can now write that the force acting on this elemental part can be the F is now equals to G. You can see what I'm saying. The one on this mass, we have M1 multiplied by dm. Then we are taking the distance from here to here, which we can call what? Can call it distance x, which is the same thing from the point to that divided by x. Now to get for the whole body, what we now do is now we go by the integration. You need to understand this, excuse me. We go by the integration of this whole body. So we say therefore, to get this, we can say the force that we act on the whole body, excuse me, which we have a F, will now be the integration of the elemental force that we have taken, which is this should be x squared, you know from formula, inverse square law. It will now be the integration of this particular force, which we call the F vector. We are now going to take the limit from one point to another. So which you need to understand. We are taking limit. You can see what is changing here is what? The distance of separation from here to here is x. Sorry about my diagram. We should take a very, very short distance of this. I'll take the distance of this to be, sorry about this. The distance should be an elemental distance, which I will call dx. So please keep that at the back of your mind. So I am taking the force to be equals to gm dm divided by the x squared. So the integration of the whole body will now be the integration of what? The elemental part that I have what? That I have now what? That I have taken. So this is the way we do it. And this time around, we can take the what? We can now take the whole length from the particular point here, you can see, to this particular point. So we have assumed the distance from here. You don't make mistake, guys. From this elemental point to the whole body here is x. I'm going to do a lot of illustration, don't worry. So we take what? The limit from this particular point, x, to the whole length now is now x plus r. So this is the way we do that, and this is the method we use whenever we have extended body and we want to get the what? The force that is acting on extended body. So students should always keep this at the back of their mind because it is not always easy to calculate sometimes, especially for those of us that we are not used to integration. I told you to start physics, you watch the basics. Basis of integration, basis of differentiation, and the basis of vector. They are available on the page. You can always watch that. So we can take an illustration to understand this concept that we just talked about by taking a rod and classifying a rod and using that particular rod to calculate what? The extended body. I hope that will be available in the next slide. But for now, you can just keep down this note, a simple note, to get the force. Just write to get the gravitational force acting, to get the gravitational force acting on an extended body, on an extended body, we take an elemental part and integrate with respect to the whole force. What I'm writing here to the whole force is just what I have given an illustration to the whole force. So keep that at the back of your mind, because this is very, very important for us to keep at the back of our mind. So guys, this is the way we do this whenever we calculate extended body. We always take our limit of integration. And I hope I will be able to do that in illustration when we have what that's in the other part of what of the syllabus. So we move on to the next slide, and about the next slide, we have gravitational field strength for point masses and extended body. Fine. Now, before we understand that, before we talk about the gravitational field strength for point masses and extended body, we need to define what is called the field strength. Now, we can write. I think it's important. I know we have studied something like this in our early classes. And to define gravitational field strength, we can write that the gravitational field strength is defined. Gravitational field strength is defined as the ratio, I think it's better using the numerical aspect of it, as the ratio of the gravitational force, as a ratio of the gravitational force per unit mass. The ratio of the gravitational force per unit mass is called gravitational field strength. And the gravitational field strength technically is denoted by E, and it is given as F divided by M. So we need to keep this at the back of our mind, which you can say F is measured in Newton, and M is measured in kilogram. You can say the SI unit is given as a Newton per kilogram, which is also good. And if you look by this now, sometimes we can also say the SI unit is given as, you can see it as, from our knowledge of F equals to MA, remember, A is also equals to what? F divided by M, which we have learned in early classes. So we can also say the SI unit of the field strength is also given as a meters per second squared. So in that relation, we can say the gravitational field strength can also be denoted by small letter g, which you call, or more or less like what you call the acceleration due to gravity, which is simply as saying F by M. So if we consider point masses as usual, like what we have done in gravitational field force, separated by a distance of r, point masses M1 and M2. As you can see here, so we can say the gravitational field force that will act in equal and opposite direction, already discussed as F vector or force, because I need to even talk about the vector relationship of this, which I also think is important for A-level students. And for now, we can say F equals to, from what we have studied, Gm1 M2 divided by the distance of what? The square of the distance. This we call inverse square law. You put that here, you have a Gm1 M2, that is for point masses. I'm doing that now, divided by, you can see, we are taking what? M1 as one of the mass, and the other mass as M2. So I'm taking this as M1. So we can just say this, one of the M gets cancelled out. So in terms of the field strength due to point masses directly, we say it is given as Gm divided by, you can see, this is everything here, divided by, so you can say I didn't finish up here, very good, divided by r squared. Please don't make mistake. You know, the formula itself, for you not to think maybe we have an error, the formula itself, we have a Gm1 M2 is divided by r squared. I hope my students are following this. We don't need to rush ourselves because I'm being called to come, but now I have to finish what I've started. So this is divided by r squared, as in the numerator is force, which we are substituting this value. So now if we go by that, we now divided by M1. So M1 gets cancelled out. We can now say the formula for G is a Gm2, which I will take as M, everything divided by r squared. So in a nutshell, my dear student, I'm saying the acceleration due to gravity for point masses, for 2 point masses, is given directly by formula as a G capital letter M divided by R squared, which you can keep in mind. And the value from what? From the parameters of art that is given according to those that studied that area, we know the constant parameter is approximately 9.8 meters per second squared. But in some numericals, you might be asked to calculate and the value might not be 9.8. So that is why you can always keep the formula at the back of your mind. And this G is now called what? The field strength. And it's the interaction, everybody knows, between the weight of the body and what? I hope you guys are following. Sorry about the camera. And what I'm saying now is that this G, which is acceleration due to gravity, we've been hearing gravity, 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 gravity. Most of us don't even know what they call gravity. So the gravity of a body is just what acts between the what? The weight of the body and that of the earth. So the interaction that acts, the actual weight that acts between the what? The weight or the mass of the body and that what of the what? Earth. Now, also, like I said, I think I need to add that here for understanding sake that it should have been done in the previous slide. You can also represent, I hope students are here, don't mind the camera guys. Like I said, you can represent the force. That is Newton law of, we are talking about Newton law of gravitation. And about the force we've studied about, we said it is given as a G M1 M2 by R squared, which must always be point masses. If it is not a point masses or point mass, as the case may be, it will not, can you adjust the camera? It will not work, it will not be valid. So keep that at the back of your mind. So if we represent that in vector form, remember the direction of the force vector is what? You can say, remember when you talk about vector, set F vector, the same thing, please, is now equals to, this is the way we represent the vector, I'll show you, Gm1, M2 divided by R squared multiplied by R cap. And R cap is only showing the position vector of first point with respect to the second point. Remember when I explained this in the beginning of introduction to this, I said we are taking the distance of separation between the two bodies. So if you are taking the first force with respect to the other, you understand that we are saying the force exerted by the first body with respect to the other mass and the force exerted by the second body with respect to the other mass. So this is the way we relate gravitational force. So we can now say, we said both forces are equal in magnitude and direction. I talked about this. So we can now say the position vector is always the distance between what? The vector and what? And the origin. We've talked about this in the vector videos. You can check that and watch it step by step. So directly here, I can represent this one in vector form. And finally, I can say the F vector, you can keep this in mind because I know it's important. And that's why I need to talk about that. So we can say the force acting on the body here can be equals to, we can say now in vector form, can be written as Gm1 M2 divided by R cube multiplied by R what? R vector. So this is the way we relate the formula. And I want my students to keep this formula at the back of their mind as it is going to be used when force are to be calculated in coordinate system. We use this expression to calculate this. You can say, where is R cube coming from? Watch the vector video. It's very, very simple. You know that the vector, what we call the position vector is given by what? R over what? Its modulo. You know that very well. So unit vector is always R, what the vector over its what? Its magnitude. Or you say it's modulo. Anyhow you call it, you are still saying the same thing. So for now, I want you guys to keep this formula for the field strength, which is the strength of the field, or you say the gravity, acceleration due to gravity, the way you call it, but under gravitational, we call it the field strength. And you can see from relationship. Another thing I'll give to you because of numericals and illustration is that we can see from relationship now, if we don't want to waste our time, let's just compute some other quick formula that might be of help for us if we are faced with questions. From relationship, we can conclude. Therefore, in conclusion, we can conclude that what the direction of the direction here, we can say directly that here from here, we say G here is inversely proportional to the square of radius and is directly proportional to the masses. So in case you are traveling from one point to the other around the surface of the earth, you can directly say, fine, that the ratio of G is inversely proportional to R squared, that's the field strength, and G is directly proportional to what? To the mass. So somebody can give you, like, you can say if it's directly, this is like saying G1 by G2 is equals to R2 squared. You can say R2 squared, R2 squared divided by R1 squared. You can keep this in mind. Also, in terms of mass, you can say G1 by G2 is equals to M1 by M2. So all these relationships might be important in some numericals. I want students to keep all these at the back of their mind because we might be directly using this formula to solve some question in the future. Who knows? But these are short formulas that can quicken your solution to getting answer or some question. So keep that at the back of your mind, and please write it in your formula list if you have one. Now, also, we are also to talk about, apart from point masses, we are also to talk about for extended body. So to understand that, I think I will just do for gravitation. You can also do the same for force. So now directly to do that, my dear students, let us quickly scroll a little bit up, which I think is what we are going to need here for enough space and for understanding. Now, let's discuss about the gravitational, what we call the gravitational strength for an extended body. Gravitational strength, gravitational field strength for an extended body. So about this, we can write that just like what I've talked about in the gravitational force for an extended body, Newton law of gravitation does not work for that. And whenever we want to do that, what we do is we take the integration. To understand this very well, we can take a rod. Let's just illustrate something that is quite different from what we have been talking about since morning. Understanding, say, because of our advanced students to have a good knowledge. Let's say we have a rod here of mass m, according to the question, and length of rod from one point to another is given to be L. Diagram not drawn to scale. And outside the rod, we have a tiny mass. You can see a point mass. We have a point mass at this position P, we have a point mass. And the question asks us to find the gravitational strength of this particular body. As you can see, this is an extended body because it's not a point mass. The rod is having a huge mass. And to calculate what the field strength of this particular stuff, like I said, we have to take an elemental part. An elemental part, or you say you want to take an elemental portion. So if I take an elemental part, my dear student, I'm taking this element. Elemental part means a small section. And when I integrate the small section with respect to the whole section, I'm going to have what I need. Sorry about the camera image, just have to manage it. And I'm also sorry for the beginning. I don't know that the microphone is not turned on, and that is why you are hearing various noise from the surrounding. I hope by now you can hear me clearly. And sorry about that. Please, you can use earpiece for the beginning, and from now to the end of the class, it should be a very good class. Now, directly, you can also look into it from this aspect. I'm taking an elemental part, which I'm going to call, I'm going to call dm. So elemental part dm is taken, and from that particular dm, we are taking place initially. This was separated by a distance of r from the question, just for us to have a good idea. Sum between this particular thing is r. So the distance between point masses and the extended body was given to be r. So because it is extended body, we cannot use the direct formula of gm by r squared. And the reason is because of this extended body. So we are taking an elemental section of dm. And when we take the elemental section of dm, definitely we know that for the distance, we are going to have another part which we call ds. So directly, look at what I will do now. And I know I have to go by the gravitational field strength. We always point in the direction. Please keep that at the back of your mind. It is quite important. You know that very well. it will point in the direction of where you have taken that elemental part. So this is the direction of my, you can see, of my gravitational field strength, which I call what? dg. It is pointing towards the direction of this. So now directly I can say from here, I'm taking an elemental part of the M here with respect to what? To this. Then the distance in which the M, the elemental part I'm taking to the what? To the point P, I'm taking that part as what? The distance from there, just like what I did in the previous slide, as X. Just keep that at the back of your mind. So, and because I'm taking what? Just a single part, I call what? dx. Keep that at the back of your mind. So this is dx, short part. So I can say the dm now, dm will now be equals to, I am only taking this small portion. So the m small portion will be the whole mass of this divided by the length with respect to what is changing, which is the x. Now, what I've done is just like saying if m is equals to L, then dm will now be equals to what? It will be what? M over L. Then dx, which is the small section I'm taking, will be M over L dx. Let's students keep this at the back of their mind because I made substitutes. So now, like I said, I haven't done this. What I will do now is what? I will go for what? To get this gravitational force at this point, I said it will be equals to, let's continue from here. The G will now be equals to integration. Before that, let's take the short one. From formula, we know G will give us G dm divided by r squared. What's my distance I have considered here? I have only considered x squared. So if I substitute the value of dm into this, I can rewrite this equation. You can follow through. The camera is not coming well, but it's just for, I think the incidence of light on it is great, is too much. So now from here we can say directly, we can say fine. So we can say directly here that if we substitute the value of dm, we can say it is now given as G capital M. I'm just using capital M, which is the mass of the extended body. We are dividing by LAX squared. Then we have what? dx. So when I told you, if you want to get the gravitational force at what? At what? The gravitational strength at P, which technically I can call the gravitational point at P, I call it GP, for you to get that, which is what we are considering. The GP, gravitational force at P, is not Gm by r squared. It will now be integration of the elemental part we have taken, which is dg. So if we go by integration of dg, it will now be integration of Gm over Lx squared. We are taking the limit of integration from the beginning. Look at the distance from P to the rod, to the elemental part, we take as x, and distance from P, sorry, the distance of P to the elemental part we take as r, and the distance of P to the whole length we take as what? R plus L. So we are taking limit of the distance from the shortest distance to the longest distance, r plus L. So what you need to keep at the back of your mind is every other parameter remain constant except what? The dimension of x, dx. So now to do this kind of integration, it is quite easy to do, as we have studied under integration that we can bring other parameter outside. So gravitational potential at P, as we have taken the elemental part, let's bring the parameter that we don't need outside, can be Gm, I am not integrating that, over L. Then I'm taking the integration of, what did I have left? 1 over x squared, which I am taking the limit, sorry about my camera, from r into bracket to r plus L. So doing that, since this other part is a constant, it will remain same. I have Gm over L. If I integrate 1 over x squared, it is going to give me negative 1 by x. I also want to remember this. So I have, don't forget, answer to this 1 over x squared is going to give me negative 1 by x. So we are taking the limit of this from r to bracket towards r plus L. So I hope you are still following. And going by that, let us take a shift a little bit. Let's move this up a little bit. So I hope you are still with me now. In continuation to this, what we do now from there is just, this camera is just giving me issues. For full concentration, you can take it. Now here we can say in this situation now, we are just substituting the value of x because we are taking limits as r and r plus l. If you put that there, not to waste time, the gravitational potential at P, which is this point, will now be given by formula. I hope students are getting this. Just by practice, we get. And if you ask to derive, it's not that hard to derive. So what you do is just the GP at this point will now be equals to, you can see Gm by L. It's very simple to substitute. We are now taking what? After substituting the limits, you are going to have 1 over r minus 1 over r plus L. For those of you only concerned with what putting formula in your brain, this is another formula list you can keep in mind, which is also important, and you can use it directly to solve a lot of questions on this topic. So the gravitational potential of a rod, of a straight rod, considering the what the ACR point. When I say ACR point, is just the length at which it was connected to the what the small mass, is given by, you have a Gm by L, open brackets 1 over r minus 1 over r plus L. This is directly going to be used in some numericals we are going to do under the numerical aspect. You remember I told you the ones in illustration here for concept are not that good, but always watch those questions and answer bank where we do a lot of advanced questions to help students understanding how to solve questions. Now, this is not the only way you can actually do this. There are other methods, but please, this is the best way for your level to understand this. And please always keep it in mind. If you have any extended body, this is what we use. Now, if it is gravitational force, I can tell you what we change. It will just be, it will be F equals to GMM over L, taking the bracket over 1 over R minus 1 over R plus L. You can also use the same thing, the same terminologies. You understand? The only thing that will change there is just the formula that is there, which will be GMM. And you know why it is GMM, because that is always what the formula itself is a GM square over. You can see that the formula remains the same. What is changing is what R and R plus L. So please don't make mistake when you have this type of situation. And this is the way we do that for every rod that is taken from the point of what, from the ACR point. That is in which it is connected to the tiny mass at a straight line. So we can also put another consideration. There are other ways you can have it. In fact, if I want to talk about equatorial point, it's not in your syllabus. So I don't want to go to what is not in your syllabus. I only limit myself to what is available in the syllabus. But if you actually want to talk about when you get to university, you are going to talk about equatorial point. What do I mean by equatorial point? Perpendicular bisector of this length. So if I have perpendicular bisector of this length, then I have to take this thing to the point of P. Because I told you the field strength, we always point to the what, to wherever you are. I said to this dx. So I take the elemental point I saw. You don't need it. Don't let us waste time on what is not needed. So guys, I hope you have written all this formula list and you have it with you. So now we move to the next slide. Wow. Now, the next slide says the variation of gravitational field on Earth's surface. Now, before we talk about variation on gravitational field, we have discussed in the previous slide that the gravitational field strength, which we call G, is given mathematically from calculations and parameters as what? 9.8 meters per second squared, which I hope you might have studied in your early classes. Now, if not, you can keep it as a note as well. So some of us do say we don't attend early classes, and this is your early classes, it's not a problem. So now, if you watch carefully, what we want to talk about here is just how G varies. And there are a lot of factors that affect why G varies from one place to another. One of the common factors in early classes is what you call weightlessness. I hope students still remember weightlessness. When a body is going up, you are going against gravity. As you go up, you continue to go. And when you want to come down, what happens? The body went to reach a state whereby what? The gravity will balance the weight. When gravity balances weight, we said you have weightlessness. When the normal reaction is equal to weight, we said the body is weightless. I hope you have studied these in your early classes. So if not, it's still not a problem. You can still use little idea from what I'll be explaining in this little bit of advanced classes, which is what we are doing here. So let's consider the Earth. As at the time I am doing this video, the Earth is still taken to be spherical. So tomorrow, the geographer can come and say the earth is no more spherical. So I am going to do my calculation based on sphere, what? Sphere, a solid sphere. So let's take that for example, and let's look into how what this varies. Now I'm taking the heart, which we talk about, the heart has been a solid sphere. Now, for consideration of what is in the syllabus, we just need to explain because it's a concept class. And looking at this carefully, without any further delay, we can say that we're considering the Earth to be sphere, and we are taking the radius of the Earth, which is from the center to any point of the Earth, as RE, radius of the Earth. I'm taking as capital letter RE. I'm taking the mass of this Earth to be ME, as you can see. And we know that what gravitational force reacts in the direction, you know that very well, like this, which you call G. From what we have studied, we said G is given as G, mass of the Earth is ME divided by RE. And from constant parameter, RE is always given as 6,400 kilometers. And GE also has its value. If you substitute the value directly, you are going to have G to be equals to 9.8 meters per second square, which is the value of the variation of what? The water, which is the value of G on the Earth's surface. So always keep that in mind. On the Earth's surface, the value of G is given numerically as 9.8 meters per second square, which most of you in your junior classes, you approximate to be 10 meters per second. Now, the second case I would only consider because I don't want you to be able to have too much of a concept so that you won't have a headache. And then about the second case, I'm going to talk about a situation whereby we have the acceleration due to gravity at a distance above what? At a distance h above the Earth's surface. Now, we are talking about gravity as you go up. You are not that far from the Earth, maybe a distance of 6 to 10 kilometers from the Earth. So we want to see how G will vary with what? With what? G will vary at that particular distance. Now keep it in mind, like G on Earth is given as GME by what? RE squared. I'm sorry about that. The formula is GME by RE squared. We have derived that in the last class or in the previous slide, as the case may be. So directly, my dear student, we can say now situation 2 at a depth h, depth means height, above the Earth. So at the depth h above the Earth, we can say same situation, but this time around, my dear student, the Earth is no more what? The gravity is above the Earth. So we can take the same situation. We say directly that the distance from here to here is given as RE, that is the radius of the Earth. Remember, RE, distance from here to here is also radius. I'm taking the mass of the Earth to be ME. I hope my students are still following. So I'm taking this from a distance of a little bit above the Earth. You can see the Earth is still spherical as at the time of this video. Now, if you look at this now, I'm taking it as h. So if you are considering the total height of this, this is all RE. So we can say the G that we act at a particular point here. Let me call the point here point P, just an illustration. So directly, why is this camera giving me issue? Let's read together. From the formula we have learned that the field strength we call acceleration due to gravity or gravitational field strength is now given as, remember, at point P now, will now be equals to G ME divided by the radius is now from this point to this point. You can see center to any point is still, this is still RE, and here we have H. So from this point P to this point will be RE plus H all squared. I hope students understand that. That's the distance that is separating the two. So directly now we can say, I'm having a lot of issues with that camera. So let me just say, factorizing this, you can say GP, I hope you are there, is equals to, I don't like the way this camera is showing. Can you guys hear me? We have GME. We are taking, this is M. So now if I factorize this, everybody at this level should know how to factorize something like this. Having issues with this, let's just Now we can factorize this. I'm saying RE square. I expand that RE all square. I'm opening bracket 1 plus H square or H by RE all square. You can confirm what I've done when you expand and factorize. This is what you are going to have for this expression, as in when you say R plus H all square. So I factorize RE square so that I can have, remember, GME by R square is given as what? The G of X. So I can write GP as GME by RE square as G of X. Are you guys following? Are you guys following? Or I said G of X, or the G of the X is spherical. Let me just say G of X. So I can write this as G of X. Sorry about that. To have a clean solve, you have G of X, then all over. I hope you understand. I'm substituting GME by Harry as the value of what? The G on the X surface, on the surface of the solid sphere. So GS, GME by R. Any issues? I can see all what you're saying, guys. So this is a GS all over. What you have left here is very, very simple. This is what you have left as a 1 plus, I hope you can see, H by RE all squared. So this is the value we use for calculating the value of the gravitational field strength at a point that is above the Earth's surface, but not far away. So please always keep this at the back of your mind, and please don't make mistake. As you can see, the value is said to be what? Also inversely proportional to the radius. Now, again, if you want to go by another expression, or you want to relate this in another way, we can use our binomial expression. So far, the value of our G of S is very, very close to, is not that large. So we can use binomial expression and reduce it. But for now, because I said I will only limit myself to what your syllabus want, and I will not talk about what is not needed. And that is why I will stop. So you can keep this expression in mind. Sometimes you can actually have an expression that will ask you for this. So you can now say finally, you can just keep it in mind like the gravitational field strength at the point H above the Earth is now given as, you can say, I've considered the point H. Should I off this camera, or should just leave it like that? Okay, so we should manage it like that. Very good. We can say it's now equals to, as you can see what we have here. So we now be equals to this expression. I'm just repeating that expression. You don't need to be panicking. This is just 1 over ds over 1 plus ds stands for the 1 on the edge, on the sphere, on the solid sphere, h over re all square. So another formula to keep in your formula list, and that is why physics is so interesting. You have a lot of formula to keep that in your formula list. So this is the relationship between at a depth height, at a depth h above the Earth surface. The relation of G is always in this in this relationship. And approximately, for some of you that you are still doing O level, so we can say the G on Earth is approximate, or approximately not equals to approximately 1 over 6 the G in space. So we can also calculate that. We can also find that, like I do tell you, there's no formula in physics that cannot be proved. It depends on your level of understanding. That is the level at which you can prove it to. So this is what I want to talk about here. We can also consider another situation, because it's not stated in the syllabus. We can talk about another situation whereby we're talking about maybe you are going down to a particular depth. You are not going down anyway. Maybe we said somebody is actually going down to a particular depth under the what? Under the Earth. We can also classify that and look at the relationship. So whatever might be the case, always keep it at the back of your mind. The relationship is still, G is always directly what? The strength is always directly proportional, inverse proportional to the what? The distance of what? The square of distance of separation. So by and large, what I've talked about so far, so good. It's just for you to know that there is always a variation, and there are a lot of factors that affect that rotation of the Earth, weightlessness, which is what you have studied before in your So it varies from one place to place, and that is why they said weight of the body also varies from one place to place, whereas the mass of the body will always be the same. So we move to the next slide. Yes, about the next slide, this should have been talked about immediately after. I don't know the arrangement of this. Like I just tell you, I'm not the one in charge of arranging slides. Now, this should have been talked about when we talked about the gravitational force. Now, about Newton's law of gravitational force, already discussed, we said the force acting on a body is given as a Gm1 m2 divided by r squared. And if you want to write it in vector form, I said it is given by formula Gm1 m2 divided by r cube multiplied by r what vector. So keep this in mind, like I said in the other video, that is going to be used directly for solving questions. Now, talking about law of superposition, we have talked about this under the topic of forces, and it is only applicable when forces are more than two. They are going to superimpose. In fact, because we said the force that exists between gravitation or between masses in a gravitational field is always an attractive force. You can also keep that at back. I told you the attractive force. That is why we always make sure when we want to talk about them, we use what attractive force. Please keep that at the back of mind. It's quite important. Sorry about that. I need to just put this in silence so that I will not be disturbing the peace of the class. So now the next thing we can still keep at the back of our mind from here is that we want to consider where the cases whereby we have more than one forces, more than two forces. So we can just take a point, a test mass. So taking a point, let's do that together. We take a point here. We say the point here. Let's say test mass. I'll take it as maybe the point of test mass m naught. I'm just speaking according to my discretion. Is separated from a particular point, another point here, where we are calling, let's say the distance from here, we have another point, whereby we have another mass, another point mass. Let's say this point we have directly straight to this. Let's say we have point mass of m1. We have another point here, m2. We have another point here, m3. So we can go for the distance of separation of each of them. So the distance from here to m, or from this point of origin, which I call the test mass, I take that one as a R1. I'm looking at this one from this point to this point, I take it as a R2. And from this point to this point, the camera is not even helping me at all. I take it as R3. So I can now just put those points I've talked about for us to understand law of superposition of force. It's just a simple illustration. So from here to here, we are taking the distance of separation as R1. From there to here, take it R2. And from here to here, we take it as R3. As we have studied now, so we are taking it with reference to what? With respect to what? Point of origin, which is m naught. So now we can say the force acting, the sum total of all force, summation of all forces, which we call the law of superposition of this one will be the force acting on the first one, m naught to m1, which is F1. I take that there's one acting from m naught to m2. I take the force as F2. And the third one from m naught to m3, I take as F3. So directly we can just write it anyhow. F1 is, remember, Gm naught m1 divided by r squared plus the second one is Gm naught m2 divided by r2 squared. This is r1 squared. This is r2 all squared. And the last one, the same thing, Gm naught m3 divided by r3 all squared. So this relationship we set for the sum total of all forces acting between different masses or more than two masses from a point of origin, this is what we call the law of superposition. So you can see that all these one, they are going to what? There exists an attractive force between them. And that's why we said gravitational force and what? Attractive force. Every one of them we are going to meet at a particular at a particular point, F2. I hope you understand what I'm writing, F1 and F3. So the attractive force that exists between different masses is combined together using the law of superposition and using the law of universal gravitation. And this particular thing is what we call the summation of all forces acting on a body is called what? The law of superposition. And this is the way we do that in numerical. You can as well keep this in your formula list. So we move to the next slide. I'm not going to waste your time. Like I said, it is all about details, explanation, because we are still going to do some illustration, which will still help you to understand it. So the next slide. Wow. Now, about the next slide, we can just write gravitational potential, or basically say gravitational potential energy. Now, you can write for the sake of writing and for the sake of understanding that gravitational potential energy. So say gravitational potential energy which I can short as GPE as I move on. Potential energy is defined. Let's get down a note. Is defined as the work done, for a good definition, as the work done in bringing a mass or a unit mass or a test mass from infinity, I think this is good, infinity to a point inside the gravitational field. So students should keep this in mind that this is the definition we give to that. But basically, you can also give this definition, which is common in your test material, as trying to adjust the camera. So we can also say the gravitational potential energy or gravitational potential is also defined as the ratio, just write the ratio, I think this is better too, of potential, the ratio of potential energy. I'm defining gravitational potential, please. Yeah, the ratio of potential energy per unit mass. So now, if we say that, we say gravitational potential is now given as V, numeric in symbol, and is given by potential energy. You've not talked about that as U divided by mass, as you can see. So we can say this U is the potential energy, which we've talked about work energy and power. You remember potential energy in conservative field and the non-conservative field, which depends only on the what. Does not depend on the axis, only depend on what the potential, and that's talking about conservative field. But we are not talking about that here, though we need the knowledge also to understand other things, which is important. So what we are saying now here is that if we have a region, for example, just given an instant, and we have a region inside this particular field, and we have a particular mass now that is placed at infinity. So if I'm bringing this particular mass to a point inside this, the energy required to bring that particular mass from this region to a point inside the what? Inside the field is called the gravitational potential energy. Gravitational potential energy. So that is the way we define that. So the most important thing that is required here is that what you are actually saying, the work done. Another way you can talk about, because work is doing, you are doing work because you are moving something from one point and you are covering a distance. We've talked about this on that concept of work, energy, and power. So the work done in moving it is called the energy. Now the potential is what you can see the way I've defined here. I said the work done. So work done, another simple way to get it, and not differentiating. Work done is force times distance. Everybody knows that. Since work done is force times distance, You know, we are talking about gravitational force. We can say the work done. Force is now equals to simple way, work divided by the distance. So here you can just substitute the value, or you put the value, then you cut. We are going to see what we are talking about. So another way to do that is just using this one and use this one to represent. So this is the way we relate this. I don't think this should be a problem for us. And if we want to relate it in terms of what point masses and test masses, we can derive the formula directly by this. You know what force stands for. So the work done is just directly, force is always Gmm by r squared. You are multiplying by the distance. Now I'm taking as r. 1r gets cancelled out this. So you can say the work done is always given as Gmm by r, which is a simple way to get this, which I believe you have studied in your early classes. Sorry, because I'm rushing. I have a lot to fry. I have fishes to fry. So you can say the potential energy is given by the formula Gmm by r. So you can also keep this in mind in your formula list, because sometimes you can talk about this, and that is why we need to talk about this. So guys, let's move to the next slide. I don't want to waste time because I am actually short of time. So this is the illustration part where we are going to solve question. And under this illustration part, we are going to talk about the question that was given or was said by my students with respect to what we have studied. The second part of this is where we are going to talk about satellite motion. Under that, that's the second video. Talk about your escape velocity. We talk about satellite parking orbit, Kepler's laws, and the rest. So let's quickly talk about deals with this illustration. Now, about this illustration, the first one we have, given that the gravitational constant is 7 times 10 raised to the negative 11 Newton meter square per coulomb square, what is the force of attraction between 10 to the power 6 kg mass of copper hanging 1 meter away from 10 to the power 3 kg mass of iron? From what we have studied, I'm sorry I'm rushing, we can say the force of attraction, which is gravitational force, is giving us G m1, m2. We are dividing the value by r squared. I hope my student can finish this by direct substitution. What is gravitational constant? Given 7 times 10 to the power negative 11. We are multiplying that by the first mass is 10 to the power 6. The second mass is 10 to the power 3. We are dividing the answer by this distance of separation, which is given in this expression as 1 meter, as you can see. So 1 square is still going to give you 1. So directly, my dear student, you can say the answer to this is 7 times 10 to the power 6 plus 3 is 10 to the power 9. Negative 11 plus 9 is 10 to the power negative 2. Then the force is always measured in Newton, which is very important for you to put. I hope students understand this, and I hope you are getting what we are talking about. Now, about the second question, we have a missile, a missile of 400, weighing 400 Newton on Earth's surface is shot into the atmosphere. You can see that's like a height above the earth. Of altitude, we have the height of this as a 6.4 times 10 to the power 6 meter. Taking the earth as a sphere, just like what I have explained, of radius 6.40 times 10 to the power 6 meter. And assuming the inverse square law, very good, what will be the weight of the missile at that altitude? As I've said, I said, for every relationship we set, if you remember the formula we derived, we said the G is always what? Is always inversely proportional to the square of radius. So I haven't said that. I told you if G is inversely proportional, if we take the first one as G of Earth, the second one as G of atmosphere. So because it's inversely, remember the way I've told you, it will be R of atmosphere only square divided by R of Earth only square. So this is just direct relationship you can do, neglecting the all other parameters that is given to you, and you can always do that directly. So then, yet again, you can also relate this in terms of force. You remember the way we relate force with respect to G. So now, because in this case, we are relating force, and I've given you how to relate force, because force is proportional to mass. Remember that too. I hope you remember. So we can say when we are dealing with force, it will be the first force over, which is the one on Earth, over the one in atmosphere. I hope students understand what I'm trying to relate. I just want to make it short instead of saying I want to be bringing out what is too much. So anyone that goes with what I want to do. Now, radius are the distance. Don't bother about that. Here, this is the distance. By force and mass, you can see, you can also say force in terms of mass. Do you know that F equals to ma? We've also talked about that when we talk about F is also proportional to what? Gmm by r squared. So I'm saying force is proportional to mass. So if I'm going by G2, I can also say this is also ME over, I'm just giving this, you don't need all this, ME over what? MA, considering two positions, one in the atmosphere, one on the earth. So directly, my dear students, solving this, you can just put the parameter. Let's take the radius of the atmosphere. The altitude, which I'm comparing two things that goes with what I have, 6.4 times 10 to the power 6, all is square, or let's just say over the R on the earth. The R on the earth is, okay, this is taking the earth as a sphere of radius. R on earth is 6.4 times 10 to the power 6, both here, all is square. I'm relating these two with respect to the what? To the forces. So I've taken atmosphere first. Now, if I want to take, I will take Earth first. That means I'm going with the mass of the Earth divided by mass of the atmosphere, or the force of the Earth, or anyhow you want to take it. Mass I'm taking as force. So here I'm taking, let me write it as force. For understanding's sake, I have 400. You can see in this case, I have taken the atmosphere first before Earth. Then in the other case, I will take the Earth force from relationship divided by what I'm looking for. I'm looking for the force or the weight, which is the mass, at the Earth, so at the atmosphere. So that is MA. So directly, I can just substitute or use my calculator, or I can see that these and these will get cancelled out. 1 squares are 1, if I'm not mistaken. This is 1 square, as if these parameters are correct, 6.40, 6.40. So I think it will not change from what I have here. 1 squares are 1. That means MA is also equals to 400. Please confirm that, Newton. So that is what I have from what let me confirm with my calculator here. I should have calculator from what I have here. It is very easy to confirm something if you don't want to make mistakes. So we have, I think the parameters are correct. It's what we have here. Yes, it's absolutely correct. Please note that because calculator is giving me, yeah, it is 6.4. I was thinking 1 is minus 6, because if you are talking about something like this, or let me see, provided I don't make a mistake in my interpretation, because I have a missile was weighing this on Earth's surface, is short to the atmosphere, and oh, look at that. Now, sometimes shortcuts might be funny. I think I have an error because it is now in the atmosphere. And what it is now in the atmosphere, remember, the formula will change to R will change. So we need to know to R plus. I don't want to use direct formula that we derive here. Remember, there was a formula we derived, which is what I want to show you now. This is the particular formula we have derived, which we can use directly to get the answer. But I want to use shortcut, and shortcuts don't want to work because I did not interpret well. So the value of the radius above the Earth, you can see above the Earth, that is atmosphere now, will be R plus H, which was what I used to derive my formula. So I could have actually made mistake there. It will be 6.4 times 10 to the power 6 plus 6.4 times 10 to the power 6. Nobody's above error anyway, but thank God I was able to spot my error. So here, and why I was able to spot is that I'm seeing the answer is the same, which I know there must not be the same value. Sure, you understand? That was how I was able to spot that there's an error, because some of you want to know how teacher knows if they make mistake. So what you can do here is just to multiply by 2. You can see it's just that you are adding, you have 2 plus 2, 4 plus 4. Let's say this times 2. So you can just do that. So just say 6.4 times 10 to the power 6. You are multiplying by 2, and I think this should give us 2 4s are 8, 12.8 times 10 raised to the power 6 will be the second one. So I will just relate the same formula now with my shortcut. I still don't want to use that with formula because it will give me what? Long process. So from what I've related, I know if I take R of the atmosphere first, R of the atmosphere is this 12.8 times 10 to the power 6 divided by, I'm taking the radius of the Earth. Earth is 6.4 times 10 to the power 6. Then is equals to, I took atmosphere here first, So the mass of the Earth is what I will take first. Weight of what will be the weight of the altitude? Weight of the Earth was given to be 400 over that of the altitude. You can see from my relationship formula, which I think is very, very fast for us to solve with. So here directly I can cut 10 to power 6 cancel out. This here 1, this here 2. And don't forget again, I will have scaled this up yet again. There is a square. RA square over RE square equals to FE square over FE over FA. So please, then here I can say this gets cancelled out. Then I have 2 squares are 4. And say 4 WA is equals to 400. Sometimes you need to be careful. So WA is equals to 400 divided by 4. So directly we have our answer to be 100 Newton. So which is the question answer, my dear student? And that is very, very correct. So that is the way we relate. Be careful about when you are relating this expression, like I've given you in the concept class. More of all these questions will be shown in later part of the numerical physics. So the last 2 set of questions here says that the Earth is 4 times the size of the moon. Fine. And the acceleration due to gravity of the Earth is 80 times that of the moon. The ratio of the mass of Earth to the mass of the moon or whatever is that. So now Earth is 4 times that of the moon, and this is Earth, 4 times that of the moon. Gravity is 80 times that of the moon. We are looking for mass. So let's just relate what we've studied. We know when we relate G, we know if we are considering Earth and moon, G of Earth divided by G of moon, just what I did just now, must be equals to, when we compare which radius is inverse, that means radius of moon over radius of Earth, all square, which is the same thing as when we compare it with mass. Mass will be directly mass of Earth over mass of moon. So this is the way we relate the relationship, which we have taught, which is just what I just solved, not quite now. The camera is back to normal magic at the end of the class. So directly now, we just need to follow the trend of the question. We don't need to waste time here. Mass of Earth is 4 times mass of moon. So mass of Earth is 4, mass of moon is 1. I'll just put it that. And the acceleration due to gravity of the Earth is 80 times. Gravity of the Earth is 80. Gravity of the moon is 1. Are you following? Is that of the moon. The ratio of the mass of the moon, mass of moon, mm, ratio mass of Earth, me. So if I'm getting mass of moon over mass, I'll just interchange what I've written here. I don't know it was in this way. So just reverse mass of moon over mass of Earth will be equals to G of m of moon over G of Earth, and you multiply by, I'm just doing that directly, which is also the same thing as, let me write it the way it is written, r radius of Earth over the radius of, we said the radius of the Earth, okay, the Earth is 4 times. This is not mass. 4 times stands for radius as the size. So we just need to keep that at the back of our mind. So radius of the Earth over radius of the moon all square. So this is the relationship you want to set. So just go for what you need. This will be a direct something. So I'm looking for mm over me. So this is what I want. Gm is 1 over ge is 80. I can multiply by re. Re is 4. 4 squares are 16 over, I have over 1. I hope I did not make mistake in this, because we need to know what we are doing. I said mm over me is equals to gm over ge, yes, is equals to re, then it will interchange over rm. The radius of the Earth is 4 times the radius of the moon. So radius is correct. And acceleration due to gravity of the Earth is 80 times acceleration due to gravity of the moon. So what I'm doing, guys, is just to verify if I don't have any issues. So now the ratio of mass of the moon to mass of the earth is now dash. So I just plug in the value. I think I'm right. This is g of this of the earth is 80 times g of the moon. So if I go by that, g of the moon is 1. G of the earth is 80 times radius of the earth is g is inverse proportional to 1 by r square. And that is why I'm changing the interface here. I hope you understand. So what I have here will be r of the second one as r of the earth as 4 over r of the moon, which is this, as it should be 4, you can say is equals to, let's just write it the way it should be, is equals to half square 4, 4 square is 16, and this is 1. So remember what we want is mm over me. So directly I can say this is the same thing as what is okay, should be the same thing as 1. This should be 1 over 16. Look at the mistake I'm making. I've seen the mistake. We just need to be careful. Sometimes it's all about being careful. Because if you are not careful, you are going to what? Make a deep mistake. Hope students are getting this. What I'm trying to do here is that I know that if I compute g with respect to radius, they are always like this. So it's inversely proportional. So if I'm computing 2, so the other one will come up and the other one. So, but if I'm computing with its mass, it's proportional to mass. Those who are actually wondering what I'm doing, this is what I'm trying to set. So I'm trying to use a shortcut, which you shouldn't need to understand. So this is the relationship. So I can say G is equals to, then you can bring constant. So that is what I'm trying to do if we have more than 1. So we can say G equals to this m by r squared, which is the formula we have derived. So if I compute that, mass of moon over mass of earth was what the question asked for. So mass of moon by mass of earth, for those who are saying they are not getting what I'm doing, that's why I'm taking this time again, is equals to, look at this. If I take mass with respect to the gravity, they are direct. That will be d of this over d of this. But if I want to take it with respect to the other one, it will be upside down because it is not directly proportional to this. It is inversely proportional to this. So, but here, this is weird, so because I want to change something now, which you are saying you are not getting what I'm changing. And what I'm trying to do here is that I can relate this directly, but this I cannot relate directly. So if I want to get this now, it will now be inverse of this, the one on what moon over that of what. So it will now change. That is why here I'm bringing E in this one you are seeing, as you can see, I'm bringing E out as on top divided by this. So what I'm trying to say now is that I am multiplying this particular value, you can see from cross multiplication, with this one and this particular value with this one. And that is what I'm trying to do. So be careful. And how do I bring this? Because you are saying you are not getting it, even though I'm taking my time. The earth is 4 times the size of the moon. Size I take it in terms of radius. So that means if height is 4, then moon is 1, because 1 times 4 is going to give you 4. Then the other one, acceleration to the gravity, which is g, was given to be, they said, earth is 80 times that of moon. So if earth is 80, then moon will be 1, because 1 times, if moon is 1, that one is 1 times 80 will give you 80. So that is why I put this and this. So directly what I'm saying is, if I say gm times rm, gm, look at this from cross multiplication, I hope you can see, gm times rm, look at gm times rm, that is 1. It will now be ge times re, because I need that. I have to do cross multiplication. So gm times rm, because I need mm of ratio me. Mm ratio me. Go for cross multiplication. So you say gm times rm. What is gm times rm? Gm times rm is 1 ratio, then ge times re, ge times re square. You can see re square. So one square is 1. That's why I'm not bothering about this. Look at this. 80 times 4 square. 80 times 4 square. 80 times 16. That should be 80 times 4 square. 80 times 16. I hope you understand it now. And that is 1260. Let's confirm that with calculator. 80 times 16 should be 1260, just to avoid a mistake. Yeah, 1280. Okay, you can see is 1280. So that would be the answer of to m. Before we are saying we want to just take it in the ratio like this, no, cross multiplication. We are taking and what? You can see m and e. So, and this is square. 1 square is 1 times 1 here, that is 1. Then this was given to be, I'm taking my time because I want you to get it. This was given to be GE, you can see 80. This is 4 squared 16, 80 times 16 is 120. So this is valid for shortcuts. Don't worry, in the numerical process, I will be so fast. Now it's for you to get it, and that is what we're taking our time. So the last but not the least, I've actually spent more time. We have talked about this. Force experienced by an object of mass 60 kilogram in the Earth's gravitational field is this. What is the intensity? We have talked that the intensity is equal to force per unit mass. If the force is 1.002 times 10 to the power 2, we are dividing it by this, which is 60, and directly I hope you can all do that. So you can say, just saying 100 divided by 60, that's 1.666. I'm just approximating directly. So I have 1.667. So we can say Newton per kg. So I hope this is direct and it's not going to cause or leak in the form of havoc. So I drop the calculator. That is the end of the class. The second part of the video on gravitational and satellite motion, we talk extensively on satellite motion. So guys, don't forget to subscribe to the channel and invite your friends so that they can also have a good knowledge of physics. See you soon and do well in the time. Bye.